Welcome to this deep dive. Today we're looking at some fascinating source material on ischemic stroke treatment. You always hear that time is the enemy, right?
Right. Yeah, that's the classic saying in neurology.
But digging into this report from Stanford, and a recent Nature paper from June 2025, our mission today is to unpack a completely new mechanical approach. Because we generally assume that if you get to the hospital in time, the technology just works.
Which is honestly a pretty dangerous assumption. I mean, the current gold standard is mechanical thrombectomy. That's threading a catheter up into the brain to snag or vacuum out the clot. But the reality is it fails on the first attempt about 50% of the time.
50%?
Yeah, it's basically a coin toss.
That's wild for a gold standard. Is that purely down to the biology of the clot itself?
Largely, yes. We're dealing with what radiologists call tough clots. These aren't just sludge. They are dense, fibrin-rich tangles of protein.
Like really brittle, right?
Exactly.
Phew.
Very brittle. So when a standard stent retriever tries to grab one, the clot often just chatters or breaks apart. The device is applying traction force, basically pulling on something that really doesn't want to be pulled.
Yeah.
And success rates for these tough clots specifically are a dismal 11%.
11%. Okay, so if pulling is the problem, the solution has to change the physics of the interaction. And that brings us to the milli-spinner device from Stanford. It's a totally different approach to removal.
It really is. Instead of a hook or a vacuum, it uses a spinning rotor. Think of a standard clot like a wet cotton ball. You try to pull the hook and it just tears.
Right, it just shreds inside the vessel.
Exactly. But the milli-spinner acts like a spindle. It catches the fibrin strands, the structural scaffolding of the clot, and it literally winds them up.
The visualization in the source material was striking. It's not just grabbing the material, it's densifying it.
Yes, it applies compression and shear forces. By winding up the fibrin, it physically squeezes the liquid blood cells out of the structure.
Which actually changes the color.
Right, you can watch it go from red to white in the lab as it compresses. It turns that fragile, wet cotton ball into a hard, tiny pellet.
And the volume reduction is massive. It shrinks down to just 5% of its original size. That has to make getting it out through a catheter significantly easier.
Infinitely easier. You aren't dragging a huge obstruction through a delicate vessel anymore. You're just removing a compact debris packet.
It's a brilliant mechanical fix. But what I found amazing is that the mechanics weren't even designed for strokes originally.
Not at all. Engineer Renee Zhao at Stanford was actually building a tiny swimming robot for drug delivery. And she noticed that as her little swimmer spun its rotors, it created this localized vortex.
Like a suction force?
Yes, a suction force. She realized the physics of propulsion could be inverted to create suction for retrieval.
Talk about serendipity.
Yeah.
But taking a robot from a drug delivery concept to a surgical tool for a human brain requires some serious anatomical reality checks.
That's where the collaboration comes in. Zhao teamed up with Dr. Jeremy Haidt, a radiologist at Stanford. His perspective was crucial because he knows the constraints of the human brain. He put it perfectly in the sources, saying 1 + 1 is like 4.
Meaning the engineering and clinical application created something neither could do alone.
Right. They went through hundreds of 3D printed iterations. Because the absolute critical constraint was that this device had to fit into the catheters doctors already use.
Because if it requires a whole new surgical infrastructure, hospitals just won't adopt it.
Exactly.
But we see miracle bots in petri dishes all the time. Getting a rigid robot through the tortuous vessels of a living brain is a different beast. How did they test this for real-world viability?
They moved to animal models targeting those tough, fibrin-rich clots we discussed. The results were published in Nature. Remember, with current technology, success rates on those specific clots sit at that dismal 11%.
And the milli-spinner.
It succeeded 90% of the time.
Going from 11% to 90% is a statistical leap you rarely see in medicine.
It is, and the immediate benefit for you as a patient is obvious. Faster recanalization means less brain tissue death and much better outcomes. The sources mentioned stroke survivor Debra Meyerson and her perspective on just how critical it is to reduce those devastating life changes.
Right, and the platform potential is what's really interesting here because a blood clot is physically similar regardless of where it is in the body.
Exactly. If you can miniaturize the physics, you can clear vessels that current catheters are simply too bulky to reach. They've formed a company to commercialize this, and they're looking at applications for pulmonary embolisms, deep vein thrombosis, and the much smaller vessels of the brain.
It really frames the future of medicine differently. It's not just about finding the right molecule, but finding the right mechanical force.
That's the big takeaway for me. We always look to chemistry to cure disease, but here the solution was geometry and torque.
Which makes you wonder how many other incurable diseases are really just physics problems waiting for an engineer to notice them. Something for you to think about. Thanks for joining us for this deep dive.